Hello everyone, welcome to project number 9, and in this project you'll have to implement a couple of vehicle route analysis, and you'll be using the same dataset that I have used in the Spark streaming hands-on exercises and in the Spark streaming videos. So first of all, let me tell you what this vehicle route analysis is and what is the dataset. It is a JSON dataset and there are approximately 50 files. The size of all the files combining together is approximately 17.34 GB, which is uncompressed size. And as I already mentioned, the total number of files or total number of datasets are 50. Each file correspond to a single vehicle, meaning that one file would contain data only from one vehicle. And this is not only going to be an exercise of PySpark streaming, you'll have to implement very complex logic using Python also. Okay, so let's talk about the vehicle route analysis, what happens. And again, this is a real life scenario. You'll find such use cases a lot if you work in petroleum organization or retail organization or logistic organization or any other such organization as such, wherein you have to monitor how the vehicle is moving. So let's take example of a petroleum organization. So let's say there's a petroleum company which sends fuel using vehicles or vehicular trucks, and the movement of the trucks are monitored very closely because of the criticality and the value of the material that the vehicle is moving, meaning that the vehicle is moving petroleum data. And as you already know, oil is very costly and it is critical and it is on demand almost all of the time. So there cannot be any scenario wherein, let's say, a vehicle is stealing the entire material and moving away. That cannot be possible. Not only that, the route that are calculated to move from, let's say, point A to point B, these are actually pre-calculated so that the movement is optimal, meaning that it takes less amount of time with less fuel consumption, and also maybe route containing lesser traffic. So you can understand the criticality of all these things. It's not a simple task to move any material, for that matter, not only fuel or petroleum products, any material from point number A to point number B. You have to calculate the route beforehand. So the route should be an optimal one, which would reduce not only travel time but also fuel consumption. The second point is that the vehicle should not deviate from the route, because if it deviates from the route, there can be multiple scenarios. One is the optimal route would not be achieved, and also there's a chance of theft. So to mitigate all those, we have organizations implementing real-time vehicle route analysis, and that's what this particular exercise or project is trying to implement. I'll not give you a lot of use cases or a lot of business statements, because the program or the implementation of the program is going to be a complex one, because you have seen in the data set that you have only vehicle ID, vehicle latitude, longitude, and the timestamp. So using that, you have to find a lot of things. So the implementation is going to be a complex one. So that's why the business use cases that you have to solve is not as much. But anyway, how the route analysis actually happens. So each vehicle would have a GPS tracker. So whatever vehicle you are using, whatever trucks you are using to send your material, to send any material, petroleum products, retail material, etc., they will have a GPS tracker and they would send their location to a Kafka topic every now and then within a certain time frame. Now, once the location is received, it would be analyzed to see whether the movement is correct or not, or the route is correct or not, whether there are any deviation or not. And that analysis would be a real-time analysis, which would be done by Spark streaming mostly. And then you can store it in a database. I'm showing you file here because in our case, it has to be both file and database. You have to implement the application in such a way that the output is saved both in file and database. So this is our use case, and in real life scenarios it would be mostly a database or a data warehousing system. So this is what vehicle route analysis is. So let's go and talk about the first use case, which is route coverage. What I mean by route coverage is that we have to find out how much distance a particular vehicle is traveling, whether the vehicle is on time or not, whether the speed is correct or not, etc. It has nothing to do with the deviation. We'll talk about deviation in the next use case, but here it is only root coverage. And as you can see, there are only two business statements that you have to implement. First business statement is to find out the total distance which is covered by each vehicle every 1 hour for near real-time dashboard. Now, why it is needed? So it is actually monitoring the route coverage, as I already mentioned. You have to find out how much distance the vehicles are traveling every 1 hour to see or to check whether the speed is correct or not, whether the vehicle pilot is taking appropriate breaks or not, etc. So that's why it is needed for real-time dashboard. Now, if I am talking about real-time dashboard, you have to understand what should be the target, whether it should be a file target or a database target. Now, I can imagine that we cannot implement a real-time dashboard using a file target, so it has to be a database target. So the distance covered has to be captured in a database. Not only that, you have to think through whether to use tumbling window or sliding window, whether watermark has to be used, state store has to be used, etc., etc. Okay, now the second use case is a little bit more complicated. First one is also complicated because I'm asking you to find out the total distance, whereas the input contains only latitude and longitude location, or lat long location. How do you find that out? 1 degree latitude is 100 kilometer and 1 degree longitude is 100 kilometer into cosine of latitude in degree. It is typically 110 kilometers, 1 degree latitude, and the information that you see in the data set, the latitude information and the longitude information, those are in degrees, those are not in kilometers, right? Because you'd see positive and negative values both, and latitude longitude are always in degrees. So you will not only have to consider the lat long information, you'll have to also consider, or you'll have to find out the distance traveled based on the lat long information, and you have to use something called Haversine formula. I'll talk about it shortly. Now let's come to the second use case or the second business statement. As per this business statement, you have to focus on only one vehicle, which is vehicle number 28. And it seems like vehicle number 28 is transporting some critical material for power station at a rural area. And the transportation is being done on 6th January of 2026. So it is a critical material because it would be sent for power station implementation or power station usage at a rural area. That's why. So the distance covered and the speed is pretty important. It also says that the material is picked at 3 a.m. on 6th January 2026 and scheduled to be dropped at 3 p.m. on the same day, covering approximately 1000 kilometers. It has to cover 1000 kilometers in 12 hours. The purpose is to continuously monitor the average distance covered by the vehicle, and that monitoring or the continuous monitoring has to be every 15 seconds. And the purpose of this continuous monitoring is to check whether the vehicle is on time or not. And whenever the average speed is below the needed speed, we'll have to flag it, meaning that we have to raise a flag saying that the vehicle is at much lesser speed than the required one, so we can send an information to the vehicle pilot, or we can have a push notification to send the flag to the pilot saying that you are driving very slow, please speed up, or you are taking a lot of breaks, please speed up, because there's a requirement to deliver the critical product within a certain time. There's a time SLA associated with the material delivery. And we can consider a buffer of 1 to 2 hours end to end, meaning that instead of 12 hours, it can be 11 hours to 14, 13 hours also. And it also says that the data older than 2 hours can be ignored because the buffer is 1 to 2 hours. So it is saying that the continuous monitoring that you have to do, in that monitoring, you can ignore data which is older than 2 hours. So considering this scenario, you have to find out what type of windowing has to be used, whether a tumbling window has to be used or sliding window has to be used, whether I have to use watermark or not, whether it will be a continuous processing or processing time based processing, meaning that whether you will use processing time in the trigger API or continuous in the trigger API. That is something that you have to find out. And there are certain nodes. And these nodes are important to implement the use case. So it is not only a PySpark implementation, it is a complex Python implementation also. So it will give you opportunity to practice Python code also. And there are three nodes. The first node says that you have to use latitude and longitude together to find the distance traveled from point number A to point number B between 2 points. Again, point number A I have mentioned it is starting at 3 a.m. and point B it is ending at 3 p.m., which is not true actually. Point B can be anything between 1 hour or 15 seconds, right? And latitude and longitudes are in degrees as always. So this is the first node. And the second node is very important. You'll have to use something called Haversine formula to find the distance between two pairs of lat long or latitude longitude. The purpose of Haversine formula is to find distance between 2 points in a sphere. See, the latitude and longitude are used to find out an exact point in the spherical dimension because our Earth is a sphere. So use latitude longitude to find out where a certain object is. It is not a two-dimensional space. It is not a plane. It is a spherical plane, meaning that it is a sphere on which we travel, and that makes things very complex because if it is a two-dimensional calculation, then it's pretty straightforward because you have only x axis and y axis. You get x points and value of x and value of y, and then you can find out the Euclidean distance between the two using Pythagoras theorem or anything as such. It is also easier in a two-dimensional or a three-dimensional plane. But the moment it becomes sphere, then things become a little complicated because how do you find out the distance traveled between 2 points in kilometers? And the points would be in latitude and longitude coordinates, or the coordinates of the points would be only using latitudes and longitudes. So that's what Haversine formula does. It is used to find the distance between those 2 points which contain lat long values for each. Point A would have its own latitude value and longitude value. Point B would also have its own latitude value and longitude value. And you'll have to find out the distance using those latitude and longitude, and that's where Haversine formula plays a very important role. I have also given a Python implementation link, and the link is from Geeks for Geeks. You can use that to implement using Python. So you can use the Haversine formula to find the distance between 2 points in a sphere, and this link will give you an idea how you can implement that in Python. And you can also find out the output, whether the output is correct or not. So you have this Omni calculator, and using this you can find out whether your calculation is correct or not. There is one more consideration, that the latitude longitude values that you see in the file contains multiple decimal points. I mean multiple digits after the decimal point. You should not consider more than 2 decimal points. You have to remember that, and the implementation should also consider that the latitude value and the longitude value should not have more than 2 decimal points. And this is the link, geeksforgeeks.org. It tells you the Haversine formula to find the distance between 2 points on a sphere. It gives you the details of the Haversine formula also, wherein you'll have to use sine value, cosine value, etc. And here there are implementations using C, Java, Python, etc. You can click on Python 3 and you'll have to use the math library to implement Haversine formula. So you can use this, or you can have a look at this code and use your own implementation if you like. It does not necessarily mean that you have to use this particular function. You can implement your own function also. And you'll have to pass the latitude and longitude values as arguments to the function. So that's what Haversine formula is, and using the Omni calculator you can check whether output is correct or not. Of course, before implementing the root coverage use case, make sure that your Haversine function is implemented correctly. And I would recommend that you create a module for this and then import the module, because in the next use case also you'll have to use Haversine formula. Along with that, I'll recommend you to use Python multi-threading to read multiple files together and send data points to Kafka. Now, why am I saying this? Because there are a total of 50 files. Each file contains information of a single vehicle. And in real life scenario, if you are having this vehicle route analysis, you will not be having a single vehicle. Obviously, the organization would have multiple vehicles which they have to monitor. That is the purpose and reason that you have 50 files and 50 vehicles. So it'll send information about all the vehicles and you do the calculation of all the vehicles at the same time. For the first point, you'll have to use all the files because you have to find out the total distance covered by each vehicle. For the second use case here, you'll have to use only one file, which is vehicle number 28. But I would recommend you that you use at least 5 to 10 files and filter vehicle number 28. That would give you closer to real life implementation experience. And this is how the implementation would be. We have multiple files and the file contains both vehicle information and route information. And using the Kafka producer, you'll have to fetch only vehicle information, not the route information. Once you fetch the vehicle info, you'll have to send it to a vehicle location topic and then use PySpark streaming application, do the processing and load it to a file or to a MySQL database. In fact, you have to actually load to both file and MySQL database. The vehicle location topic should have 10 to 20 partitions. I would recommend that you use 20 partitions. And you have to use Python multi-threading to read multiple files using a single program and send to Kafka topic. You can use, let's say, 5 threads in a single file. In that case, you'll have to run 4 programs or 10 programs, sorry, because there are 50 files. Or you can use 10 files in a single program. So you can read 10 files using Python multi-threading and send it to the vehicle location topic. So if you're reading 10 files, you'll have to execute 5 programs at the same time. And once that is done, you'll have to capture the information using the PySpark streaming application. Output data should be stored both in file and MySQL database. The MySQL database can be on Aurora, AWS Aurora, or on your local machine also. I would recommend to use AWS Aurora because that is easier to implement. If you use your local machine, then you'll have to install MySQL, you have to create the tables there, etc., etc. So use MySQL Aurora to save the output data in a database, and file can be a local file or you can store it in S3 also. So this is the first use case, which is route coverage, and you have to implement both the business statements that I had shown you in the previous slide.